Okay, so welcome back. And so now we're going to do an example. And this is going to be a good one because I haven't, I like these because this is, again, my background when it comes to probability theory. And so I've done a lot of these in grad school, and it's been a while, but this is going to be fun. And so we're going to find the probability of getting a particular score on a standardized test. And so in this case here, X represents test scores on a particular standardized test. And so we know that the distribution of these test scores is normal with a mean of 100 and a standard deviation of 50. That's what this symbolism means, okay? So now what we're going to do is we're going to find the probability of what? They want to find the probability, we want to approximate the probability that a randomly selected test score is between 100 and 200 on this particular test. Okay, and it says use the alternating series test to determine how accurate your approximation is. Okay, so again, you make sure you understand what the alternating series test and how to use it to find the error bound. Okay. Okay, so let's get started. So first of all, so A is 100. So well, let's draw a picture. Let's draw a picture. Okay, so here we know it has a normal distribution of 100, mean of 100, and sigma equals 50. Okay, and we want the probability of a randomly selected test score being between 100 and 200. So let's say, so this is A, and so let's say, so we got 200 here. So this is our A, and this is our B, right? And so we want the area under the curve between 100 and 200. That's the probability, right? So again, let's use the z-score formula, the simplified one, because it's going to give us the same probability. That's the other cool thing about this is whether we use this normal distribution or whether we convert it to the z distribution, the area between the two numbers will always be the same. The probability will always be the same, okay? Again, if you're ever interested, take a class in statistics and that'll be one of the things you study. So let's use the z distribution. So what we're going to do is, again, write out the formula. So we want the probability that a randomly selected test score is between 200 and 100. And this is going to equal 1 over, since we're using z, we want z. Okay? Oh, wait a minute. Okay, hold on. Let me do it this way. Let me write the same thing. So let's start with what I had here. So 100 and 200. Let's start with that. Okay, so we know we're going to have to integrate 1 over sigma times the square root of 2 pi times from 100 to 200, right? The integral from 100 to 200, and we're going to have e to the negative x minus mu quantity squared divided by sigma 2 sigma squared. Okay? And then dx. Okay, so we know that's the general function, right? The general function of a normal curve, okay? So now, to simplify things, let's transform this into a z distribution, okay? So this is going to be the same as if I convert it. So I'm going to draw another normal curve. And so if I use the z-score formula, so I'm going to do x minus mu over sigma. And now what I'm going to do is I'm going to take this, right? So this is going to correspond with this. Okay? And again, my picture is not the best, but so now if I plug 100 in here, guess what? That's going to correspond to 0. So I'm going to 100 minus 100, right? Because the mean is 100, the standard deviation. So remember, this is mu, this is sigma. This is the population mean, this is the population standard deviation. And so I'm going to plug both of these values into my z-score formula. This one is going to correspond to 0, which is right in the middle. And if I plug 200 in here, that's going to correspond to a z-score of 2. So that means that instead of finding the integral between 100 and 200, I'm going to find my integrals of my limits of integration are going to be from 0 to 2. So now what happens to my formula? Okay, just like I showed in the last video, this probability is equal to this, which is also equal to what? Now I'm going to put in these values. Okay, so sigma is 50, which is 1, right? Because if I stick in 1, or if I stick in 50 here and 100, I get 2, so my z-scores. But my parameter is 50. So, what happens? Oh, by the way, and here, oh, that's what I was forgetting. So in here, my standard deviation is 1. Okay, so remember, when I do my z-score formula, I'm transforming this general normal distribution with this information to a standard normal distribution. So it's going to be a z-score, so it's going to be z is normal with a mean of 0 and a standard deviation of 1. Okay, so that's what I'm doing. So what I did was I basically, instead of working with this, I transformed this into the standard normal distribution. So instead of dealing with this integral, now I can deal with the more simple integral, which is this. 1 over the square root of 2 pi times the integral from 0 to 2 now, instead of from 100 to 200. And my integrand becomes e to the negative z squared divided by 2 dz. Okay, so this is what I'm going to work with. So now, okay, now I'm going to do the Maclaurin series. Okay, oops. So now the Maclaurin series for this, and again, remember the Maclaurin series for e to the x is given by x to the n over n factorial. So again, we're going to use the fact that we know that to give us the Maclaurin series for this. Okay, so let's do that. So let's start again, before we come back to this, let's figure out this. So e to the negative z squared over 2 is then going to be equal to the Maclaurin series for n equals 0 to infinity of what? It's going to be the quantity negative z squared over 2 to the n power over n factorial. Right? Okay, so now, what happens to this? Well, if we start expanding this, what do we get? Well, let's expand this out. We get, this is equal to 1 minus, oh, let me do it this way. Let me do it this way so you can see it. Okay, so this is going to be 1 minus x squared, or z squared rather. Right, because we're using z. So this is going to be z squared. Is that right? Let me see. So 1, so that'll be z squared over 2 over 1. Yeah. So this is going to be minus z squared over 2 times 1 factorial plus z to the 4th, right? So now it's going to be plus z to the 4th over what? 2 squared times 2 factorial. So it's 2 squared times 2 factorial, then minus, now this is going to go to z to the 6th over 2 to the 3rd times 3 factorial, and then so on and so forth. And then the nth term is then going to be z to the 2n over 2 to the n times n factorial. And then it continues on. Oh, wait a minute. Oh, there should be a plus or minus. There should be a minus 1 here. Minus 1 to the 2n. Is that right? Hold on a second. Oh, no, to the n. Where is it? Just to the n. Because it's an alternating series. Is that right? Did I get that right? Yeah. Yep, that's right. And then it continues on. Okay, so again, so this is our Maclaurin series that represents e to the negative z squared divided by 2. Okay, so now we're going to plug this into our integral and see what this gives us. So now what I'm going to do is let me erase this. Oh, oops, hold on, I don't want to. Okay, so this is going to be z. Okay, so now I'm going to stick this in here. So the probability of x, so this is now the probability of x, z being between 0 and 2, right? Same probability, but now it's going to be equal to 1 divided by the square root of 2 pi. The integral from 0 to 2, and it's going to be now, we're going to stick our power series in here. It's going to be the integral from this, n equals 1 to infinity of, let me write it this way, let me simplify it. So this is going to be negative 1 to the n z to the 2n divided by 2 to the n and then divided by n factorial, and then dz. Okay. And so this is going to equal 1 over the square root of 2 pi times the integral from 0 to 1. And this is going to be of 1 minus z squared over 2 times 1 factorial plus z to the 4th over 2 squared times 2 factorial minus z to the 6th over 2 to the 3rd times 3 factorial plus z to the 8th over 2 to the 4th times 4 factorial minus z to the 10th over 2 to the 5th times 5 factorial, and so on and so forth. Dx. Okay. And so now we're going to... Did I miss anything? Hold on. No. So now we're going to integrate this. Okay, so when we integrate this, this is what we end up with. Okay, and again, we're going to integrate this term by term. And we're going to get 1 over the square root of 2 pi times c plus z minus z cubed over 3 times 2 to the 1st power times 1 factorial, and then plus z to the 5th over 5 times 2 squared times 2 factorial minus z to the 7th divided by 7 times 2 to the 3rd times 3 factorial plus, and so on. And so the nth term of this thing becomes, let me continue on, is given by this. So it's going to be 1 to the nth, and then it's going to be z to the 2n plus 1, so basically integrating the nth term, and then it's going to be 2n plus 1, so divided by 2n plus 1, and then divided by 2 to the nth times, or n factorial, and then continues on. Okay, so now what? So let's go back to what they want us to do. So we've got this set up, so we've got the Maclaurin series, and so what do they want us to do? They want us to approximate the probability that a randomly selected test score is between x equals 100 and 200. So when we integrate this, right, so this is general, but that's the same as the definite integral from 0 to 1. Okay, so this is so we're not going to have the c here because that's if we have an indefinite integral. So this is going to be evaluated, right? So we're evaluating this integral from 0 to 1. Now the cool thing is because we're dealing with 0, then all of these terms go to 0. So we don't have to do anything there. So the only thing we have to do is evaluate this thing at 1. Well, when we do that, now our probability becomes this, or the series becomes this. It's 1 over the square root of 2 pi times, now what happens to all these terms? Well, z is 1, so this becomes 1 minus 1 over 3 times 2 times 1, because that's what happens to this 3 times 2 to the 1 times 1 factorial. 2 to the 1 power is 2, 1 factorial is 1, so we just get 3 times 2 times 1. Then we get plus 1 over 5 times 2 squared times 2 factorial minus 1 over 7 times 2 cubed times 3 factorial. Okay, now what I'm going to do is I'm going to erase all of this now. Don't need that here. And I'm going to continue this on a little bit. So this is going to be plus, and then it becomes 1 over 9 times 2 to the 4th times 4 factorial, right? And it just keeps going on like that. And so this is going to be 11 times 2 to the 5th times 5 factorial, and so on. Okay, so now this infinite series becomes the probability of randomly selecting a test score, and that test score being between 100 and 200. Okay, so if we use the first 5 terms, okay, so if we use the first 5 terms, which is this one, this one, this one, this one, and this one, so we use these 5 terms, what do we get for an approximation if we just use those 5 terms? Okay, well, if we put that in our calculator, we get approximately well, actually, we have to multiply by, right, so we have to multiply by this too. So if we just do the first 5 terms and then multiply by this factor, then we get approximately 0.4922 as our probability. Now that makes sense because probability is a number between 0 and 1, so it's always going to be a decimal between 0 and 1. So this is the probability of randomly selecting a test score, and that test score being between 100 and 200 points. Okay, so it's approximately a 0.4922 probability. Okay, so now what? Well, we want to know how accurate that is. So now you're going to use the alternating series test, and if you use the alternating series test, you can estimate that this is accurate to within this. Hold on one second. I just want to make sure I didn't make a mistake here when I was writing this out. Yeah. So now, let me write it up here. Okay, so we got this. I don't want to erase this yet. And so we found that the probability of a test score being between 100 and 200 is approximately equal to 0.4922. Now, by the alternating series test, we can find the accuracy by using this. So it'd be 1 over, so it's going to be within this error, which is going to be 1 over the square root of 2 pi times oh, that's where I made my mistake. Okay. It's not 1, it's 2. I'm sorry. See, yeah, it's from 0. I must have messed up. It's from 0 to 2, not 0 to 1. I don't know if I made that mistake in my head, or because remember, it's from 0 to 2, so the integral is from 0 to 2. So the only difference is all of these need to be 2's. Okay. Well, hold on. 2 to the third, 2 to the fifth, 2 to the seventh, and 2 to the ninth. To the 11th. Yeah, 2. Okay, yep. Okay, so this is what we're going to add up. So my mistake, we're going from 0 to 2. For some reason I got stuck with 0 to 1. And but still, so we're only evaluating these at 2. And so the first 5, so that's what gives us the 0.4922. Okay, so I knew something wasn't looking right. Okay, so now this is going to end up giving us this. So this is the probability, and we're going to be accurate within this amount by using the alternating series test. So this is going to be 2 to the 13th over 13 times 2 to the 6th times 6 factorial. That's what it is. Okay? So 1, 2, 3, 4, 5. Yeah. And then this is going to be approximately equal to 0.00546. Okay, so we know that this is the probability, this is the approximate probability of choosing a test score randomly, and then that test score being between 100 and 200 points, and we know that we're accurate, that probability is accurate to within this amount, so 5 thousandths of a point, of a probability point. Okay, now, if you've taken a stat class or if you're familiar with probability theory, then we know using a normal curve, a bell-shaped symmetric curve, the empirical rule tells us that the approximate probability of being within 2 standard deviations of the mean. So that would be this right here. We know that this probability, this area, is approximately equal to 0.475. Okay, because to be within, the empirical rule says to be within 2 standard deviations, the probability of being within 2 standard deviations is 95.95. Okay, so if we take half of that, because it's bell-shaped and symmetric, if we take half of that, half of 95 gives us or half of 0.95 gives us 0.475. And so if we look at this and our margin of error, our error bound here, okay, I believe that keeps us within range. Yeah, so not bad. Not bad at all. So we are within that margin of error. Yeah, right. 40. I just want to make sure I wrote down these numbers. Yeah. Okay, that's it. Have a great day.